Hi guys. Finally, I hope this one's the one that's going to work. So today we're going to talk about the ideal gas law. And what's different about the conversation we're going to have today is we're going to talk about what happens when the number of moles of gas changes. So in the previous discussion, we were looking at gases that were confined to a particular area. So the sample wasn't going to change. We call that a closed system. Today, we're going to look at what happens when we have an open system. Our goal is the same. How can we use math to make predictions about what's going to happen or make sense of what has happened? So let's talk about the ideal gas just one more time. An ideal gas was a gas in which collisions between atoms or molecules are perfectly elastic and there's no intermolecular attractive forces. In other words, they obey all the kinetic molecular theory assumptions that we discussed earlier. So I want you to take a look at this list of assumptions. And I wonder if any of those that you looked at, you were like, wait a minute, that doesn't sound right. So mark all of the ones that you think maybe we can't assume. How'd you do? So the ones in green are the ones that pretty much all the time a gas is going to follow. We know gases are made up of particles. We know they're in random constant motion unless they're at absolute zero, which we're not going to encounter. And we know that the temperature of the gas is dependent on whatever the kinetic energy of those particles are. Now, this one down here in orange is because that it's not completely true. There's some energy stored in their bonds that can come to life as elastic potential energy, but that's not really going to have a bearing on any of our calculations. However, if you look at the ones that I've colored red here, we know that matter takes up space. That's the whole definition of matter. We also know, based on our study of intermolecular forces, that if an atom has electrons, which all of them do, they're going to have some sort of, they call them van der Waals forces or intermolecular forces that they'll exert on each other. So they'll have some attractive forces. So this one isn't completely true. And we also know that the collisions aren't going to be elastic if they are somehow being attracted to each other. So there are some assumptions that we make about gases and the way that we calculate that just aren't true. If we were to take look at three gases, actually we have four gases here, helium, neon, argon, and krypton, and plot their pressure and their volume all the way down to almost zero for both, you're going to see that they don't exactly follow the ideal gas. So look right here, the solid line is what we would expect for the ideal gas to do. But we can see that helium and neon down here at very low pressures, very low volumes. So when they're squished together, their pressures are actually higher than we would expect them to be. Well, that's because matter takes up space. And so they aren't going to be able to move around as much, where in a larger container, they're free to move and the actual volume of the gas doesn't seem to make a difference. But here, they're going to bounce around and bump into each other a whole lot more than they would in a larger system. And so those pressures are actually higher than we would estimate. Also, if you look at argon and krypton, and I've put their atomic numbers here to help you out, argon and krypton are way bigger than helium and neon. And so you'll notice that, wait a minute, they take up more space, so why are they at lower pressures? Well, if an atom has more electrons, what do we know about their intermolecular forces, about those London dispersion forces? They're going to be a lot greater. And so if we have large gases, they're going to stick together a lot more. And therefore, if they're sticking to each other, the velocity or the momentum with which they hit this side of the container is going to be lower. Their pressure is going to be lower than we expect. We also see this intermolecular force at play when we look at some gases that we know are actually polar. So again, here we have hydrogen gas, which is really, really close to ideal because it doesn't have electrons to speak of, and it's very small. It doesn't take up much space. So it's going to be very close to ideal. But if you look at something down here like hydrochloric acid, we know that's going to have a large net dipole moment, and ammonia even more, because not only does it have a net dipole moment, it has hydrogen bonding going on. And so these gases, I like to say, are very sticky. And so their pressures are going to be way below until we get out here where their volume is large enough that those gases can move around and act a little bit more ideally. You may see graphs like this in the future. You might even see those crop up on an ACT exam. So it's a good idea to kind of have a little bit of an idea about what they're talking about there. Okay, for this reason, when we look at the relationship between pressure, volume, number of moles of gas, remember, is N. I'll talk about R in just a minute, and the temperature, we have to put in these correction factors. And so the equation that you're looking at right now is the actual gas law equation. And we have these little factors that we can put in there. I call them fudge factors to account for intermolecular attractions of the gas. And so these are going to have to be experimentally determined, or for the size of the atom. Again, we'll measure the atoms, and so that B factor will be its size. However, remember we just said, if we look back here at these graphs, especially this one, as we get to larger volumes and lower pressures, which is what most of the world operates at, they're going to behave ideally. So we have the luxury of ignoring these factors because those numbers are going to be so small. So what we end up with, that's what I just said. So what we end up with is the ideal gas law, which you can use for almost any calculation. Now, as you move into engineering applications and things that are happening at really high pressures and really low temperatures, you will have to go back to that other equation. But for almost everything that we're going to do, R is what we call the gas constant. So remember when we looked at data the other day and we kept multiplying the volume times the temperature at all the different variations, and we kept getting a constant? Same thing happened when we did pressure and volume and number of moles and pressure. And so Avogadro, our good friend that came up with Avogadro's number and how to count the mole, also helped us incorporate R into a value that reflects all of those constants. So if we look at if we think back to the closed system again, we had these rules that this would be Boyle's law over here, the relationship between pressure and volume. This would be Gay-Lussac's law, the relationship between pressure and temperature. If we combine them, we got this combined gas law that the pressure, volume, and temperature before the change is going to be proportional to the pressure, volume, and temperature after the change. And if we throw in the number of moles, if we're interested in that in the closed system, then moles is going to go on bottom. But all of these, when we use the combined gas law, we're assuming a closed system. Gases can't come and go. And so it's proportional, and we're able to do this. But in most cases, our system is not going to be closed, and the number of moles of gas could change. So we're not going to have this proportion on the other side, and we're going to have to take measurements of the final conditions. So if we can measure, if we look down here at our actual gas law, if we can measure, let's say the volume, that'd be pretty easy. I know how big the container is that my gas is in, and I can measure the pressure with a pressure sensor, and I can measure the temperature. Then I can figure out how many moles of gas I have in my container. Let's talk about R for just a minute. And when you get into higher chemistry in college or in AP chemistry, we'll go over a derivation to see where we get this liter atmosphere mole Kelvin for the units on R and kind of how we get R. Unfortunately, in our compressed time with our weird circumstances, we're not going to be able to do that. But if you will just trust me, you can go look it up and double check that it's been determined that we can apply this gas constant 0.0821. In some texts, it will be taken out one decimal point further where it's 0.8206. And these are liter, atmospheres, moles, Kelvin. And so those are the units on that constant. Now, if you look at other texts and other applications, if you're measuring in kPa, that constant's going to be different because remember, atmospheres and kPa are a different number. So you may see the number 8.314 liter kPa per mole Kelvin. So you can use either of these. Here's the thing. If you're measuring in atmospheres, you have to use this number. If you're measuring in kPAs, you have to use this number. Also, notice the volume is in liters, so it can't be in milliliters. And again, Kelvin, we're kind of used to converting temperatures to Kelvin, but you have to have your temperatures in Kelvin, okay? All right. So let's do an example problem. How many moles of ammonia gas are contained in a 2-liter reaction vessel that's measured the pressure at 3.5 atmospheres, and we know the temperature is 135 Celsius? We're going to use our equation, PV equals nRT, but we want to know how many moles of gas. So we're going to solve for N, which is going to require a little bit of algebra to switch it around. Now, let me say really quickly, it's okay if you wanted to plug in RNT over here and just solve for N, if that's the type of algebra you like. I like and think it's safer if you rearrange your equation while you just have letters. That way you're not moving around lots of big numbers and units and then lose track of what you're doing or maybe put a decimal place in the wrong place. You get all your switching around done with your variables, and then you can plug in and solve. And that's a really safe way to do it. Okay, back to our problem. So we need to figure out what is our pressure, what is our volume, R is 0.0821 liter atmosphere mole Kelvin, and temperature we're going to have to convert. Do you think you could do that calculation on your own? Hop over there real quick, do it, and let's see what you came up with. Okay, so first we had to convert to Kelvin, and then if we plug in our numbers, you should have gotten 0.28 moles of ammonia. Now, I know that I rounded that number quite a bit, but notice your sig figs up here. I have 2 digits, 2 digits, and 3 digits. And by the way, never, ever, ever use a constant. So your R right here has, in this case, I used the 0.06. So you've got 5 digits that will never be used to determine the number of significant digits you have. Constants and reference values are never used. Okay, so this is kind of a nice little table. If you want to take a screenshot of it and put it in your notes, that'll help you get at just about any kind of problem that you want to solve. Okay, here's another one for you. Read the problem carefully. Think about, do I have any conversions I need to make? And what constants do I need to use? Give you a minute to go ahead and do that calculation, and we'll see what the answer is in a sec. How'd you do? Okay, again, we decided to find moles, so we rearranged our equation. The step, though, that we had to do that was a little bit different is we needed to convert grams because they asked for what the mass of propane was. So remember, to go from moles to grams, we're going to multiply by the molar mass. Okay, and that's what this calculation is right here, just calculating the molar mass of propane. That's not so hard, is it? It's just a new equation that you're going to be plugging numbers into. And the biggest challenge is to go through and match. Okay, so 2 liters is volume. 1 atmosphere is P. It's my pressure. Okay, here's another one. All right, so what are we solving for this time? Not N moles, we're solving for pressure. So we rearrange our equation so that pressure is equal to nRT over V. Plug in our values. Again, we had to convert temperature because it was in Celsius to Kelvin. And our 0.0821. I know I didn't put in the units there because it was getting, it looked kind of confusing, but those are liter, atmosphere, mole, Kelvin. All of my units will cancel out and I'll end up with atmospheres. I hope this is feeling pretty easy. Like I said, it's just another equation. You're going to hunt for the variables that you need, plug them in, and solve for the one that's unknown. Here's one more. This time we're looking for volume. What volume at 1.73 atmospheres and 112 degrees Celsius are produced by 74.4 liters of oxygen at 0.583 atmospheres and 21 degrees Celsius? Oh, so you've got a few steps that you're going to need to work through on this one. How did it go? Okay, so the first thing that you're going to have to do is you're going to have to convert liters of oxygen to moles of oxygen, because remember, we can't do stoichiometry in liters. Only if it's at STP or if the, how do I want to say, the pressure and volume and temperature don't change. And unfortunately, we have changing conditions, so we can't use our trick of liter per liter because they're not going to be the same. So step number 1, we're going to go in and, well, actually my step number 1 is I like to convert all of the temperatures right off the bat so that I have everything in Kelvin. Then I needed to figure out how many moles of oxygen do I have. So they gave it to me in liters. And here in step number 1, we're going to convert to moles. Then once I know the number of moles of oxygen, I can use stoichiometry and multiply by the mole ratio to find out the number of moles of SO2 that's produced. So if in this first part, I have 1.797 moles of oxygen, I know that it requires 3 moles of oxygen for every 2 moles of SO2. So here's my mole ratio right here. And when I do my math, I find out that 1.198 moles of SO2 are produced. Now the problem asks me for the volume of SO2. So in the next step, I need to use my ideal gas law and solve for volume. We haven't done that one yet. So I isolate pressure over here on this side and plug in my numbers. I just found out that I had 1.9198 moles gas constant. I've already converted my temperature from Celsius to Kelvin, and that should say 385, not 285. And yeah, because see up here. And then this is given to me in the problem, 1.73. And I end up with 21.89 liters. Okay, so that wasn't too bad. It was a little confusing when you have to go back to stoichiometry, but everything we do is about reactions. So what if there's more than one gas present? In the problem we just worked, we can see that there are going to be 2 gases present in the products. We started with just oxygen as a gas. This solid, or I'm sorry, this liquid isn't going to contribute to the gas pressure at all. But in our products, we have 2 gases. So what do we do when we have 2 gases? There's a couple of different approaches that you can take. You can calculate both of the pressures and add those up, or you can calculate the total number of moles and add those up. We're going to use the first approach because I want to introduce you to a concept called partial pressure. So if we were to think back to our kinetic molecular theory, we know that each gas is applying pressure to the sides of the container. Okay, when it bumps into the side of the container, that's where the pressure comes from. And we know that all of the gas particles in a sample of gas are at the same temperature, same average kinetic energy, but their speeds are not the same. And we know the larger ones are traveling slower than the smaller ones. And if they're traveling so slower, it means they're going to bump into the sides of the container with a different velocity and therefore a different force. And if they have a lower force, then they're going to have a lower pressure. Or if they have a higher force, they're going to have a higher pressure. So all the gases inside will not be at the same pressure. It depends on their molar mass. Okay, so it makes sense that what we're going to have to do is figure out the pressure each gas, each type of molecule is exerting, and then add those up to find the total pressure that those particles are exerting. And we just call this partial pressure, Dalton's law of partial pressure. Each gas has its own pressure, and they add up to make the total. So let's go back to our problem. They want to know what the final overall pressure in the container is going to be, because we know that we're not just going to make SO2 gas, we're going to also make some CO2 gas. So what do we already know? In the last problem, we found out the final temperature is going to be 385 degrees Kelvin, or just Kelvin. We know the volume, we calculated that as 21.89 liters. Gas constant hasn't changed. And we already calculated the number of moles of oxygen that we began with, which was 1.797 moles. So what we need to find out then is how many moles of CO2 are produced, figure out the pressure of CO2, and then if that stupid little thing would go away down there, we can add up the total pressure of the gas. So the first step is to calculate moles of CO2. Since we know the moles of oxygen was 1.797, we look here at the mole ratio. So we have a ratio of 3 oxygen to 1 CO2. So we're going to multiply here by the mole ratio, CO2 on top, so that moles of oxygen cancels out. And we discover that we have 0.599 moles of CO2. So piece number 1 found. Now we need to convert moles of CO2 to pressure of CO2. That can be done by plugging into the gas law, and we discover that we have 0.865 atmospheres of CO2. We already knew how many atmospheres of SO2 we had. We found that, or we were given that in the last problem. So if we add those together, we find out that we have 2.59 atmospheres of gas total in the container. If you'd like to watch a little bit more about this, go to Crash Course Chemistry. Paint green is a lot more fun than I am, and good luck. Stop this. Screen testify.